Um, okay, so let's start with calculating the partition function of an ideal gas. Uh, this basically follows the class which was done on the 8th of February 2023. So in general, the partition function, which is 1 by h cube. So the partition function is basically a sum over all microstates of a system which is in contact with a heat reservoir and all the possible microstates that it can take. And if you are talking about an ideal gas, then the different microstates are defined by not only the different positions that the particles can take. So the if at a fixed momentum the particles keep changing their different positions, they all correspond to different microstates. Moreover, the particles can also collide and exchange momenta with each other. So each of the particles can have different momentum. And when the different particles have so a set of coordinates, both momentum and space, real space and momentum space. If you specify the positions and the momenta of all the particles, that corresponds to one microstate. One microstate corresponding to the ensemble of all possible microstates that are possible. Now we are doing a canonical ensemble. We calculate partition function for a system which is in contact, which is in thermal contact with the reservoir. It has n particles, has occupies volume V, and however it can exchange energy with the reservoir, so its energy is not fixed. As a consequence, the total energy then uh, the system can have can fluctuate, can have different values, but higher energies of the system are penalized in terms of probability of occupying that particular microstate, uh, because the probability that a system will occupy a particular microstate with higher energy E is proportional to e to the power exponential minus beta, beta being 1 by kBt. So this beta into the energy of the microstate, right? And divided by z, the partition function. And our aim is to calculate the partition function, which is summed over all possible microstates where all different values of momenta is possible and all different positions are possible. And this is the expression. This will be the expression for the partition function, where each particle, so suppose P1 corresponds to the momenta Px, Py, Pz, hence D3P1. So you can also write D3P1 corresponding as dpx of particle number 1, dpy of particle number 1. So each particle can have different values of momenta P1, P1x, P1y, P1z. So you can write that as well. On the other hand, dpx, dpy, dpz can be written in the spherical polar coordinates as an element of volume, and then you can write it as d3p. Similarly, d3q1 corresponds to the real space coordinates of particle 1c, which can be dx, dy, dz, because you're going to integrate over all possible microstates. On the other hand, you can also write this dx, dy, dz can be written in spherical polar coordinates as d3q, right? I mean, you're just writing in different coordinate systems, and what the aim is to average, to calculate, to integrate were all possible momenta of each of the particles, where the sum, where the sum of energies corresponding to a particular set of momenta of n particles will give a certain value of the energy. And if the coordinates, if the momentum coordinates of all the different particles are such that it corresponds to a very high energy, then that will appear in e to the power minus beta h, right? And this n factorial, it stands, it's there because we know at least today, not when it was first calculated, that the particles are identical. So if you had particle A here and particle B here, uh, this had momentum P1 and this had momentum P2. And however, if these two particles were exchanged such that particle 2 was sitting here and particle 1 was sitting here, uh, uh, and then and particle 2 had momentum P1 and particle 1 had momentum P2, then we would not be able to distinguish between the two cases. So hence, to avoid this overcounting due to this indistinguishability, you have this factor n factorial. And why does n factorial take care of the indistinguishability is discussed in a previous class. They are confused about that indistinguishability factor 1 by n factorial, please refer to one of the previous classes. And here all that we are doing is we are allowing the momenta of each of the particles to go from minus infinity to plus infinity. And why is that? We are assuming that the system which is in contact with the heat reservoir can take different values of energy. Of course, most of the time it will have a certain relatively so its probability distribution of the energy will be sharply peaked. So it will have a particular average energy, and fluctuations about the average, as you saw in the previous classes, is relatively minimal, or rather goes as relative fluctuations in energy goes as 1 by root n. But the system can access very high values of energy with very low probabilities, of course. But that is taken care of by this e to the minus beta h factor. And we assume that the system can take higher and higher and higher energy even up to infinity. Of course, infinite energies of the system will be penalized with e to the minus beta infinity. So you will have really very low probability, right? 1 upon e to the power beta infinity will be a very large number. So it will have very low weightage, sorry, it will have very low weightage. So all the positions can vary within whatever the limits set by boundary conditions, and all the momenta can vary. I mean, rather dpx, dpx, the momenta and x can vary from minus infinity to plus infinity. And similarly, the momenta in y direction can vary from minus infinity to plus infinity, and so on and so forth. And thereby, the expression for the partition function is given 1 by h cube, where h cube again is that unit volume of phase space which we use for the microcanonical ensemble, right? So here it's d3p1, d3p2, and so on up till d3pn, and all position coordinates d3q1, d3q2 up to d3qn, right? And the Hamiltonian for the ideal gas is given by summation over each particle, or rather each degree of freedom. Let's say x, y, and z. I runs from 1 to 3n, if you like. Pi squared by 2m, right? So I runs from 1 to 3n, and x, y, z of each coordinate. And here, if it's an ideal gas, we are ignoring the potential energy term. But having said that, I again remind you that there has to be collisions. These collisions are instantaneous, are assumed to be instantaneous, because if there were no collisions, the system would never go to equilibrium. Yeah, but for the purpose of calculating the total energy of the system, the energy contribution due to the collision, whenever particles are in contact, that's assumed to be negligible. and that really simplifies the calculation of partition function a lot. In fact, this expression can be written as one. Now, this should ideally be, because you have n particles, this should ideally be 3n, as you see here, right? For every x, I mean r and p vector, you will have, I mean, yeah, so please go. So this should be n, because there are n particles with 6n degrees of freedom, and each will have an angular momentum. Uh, I mean, each particle will uh, have a phase space unit volume of h cube, and since you have n particles, you have h3n. Right now, when you integrate over all the position degrees of freedom for each particle, d3q1, if you integrate over all the volume, so the x can take from whatever the size of the box, to whatever is the x extent of the box. If you take it to be a box, I mean cubical box, and if it is y, similarly, it can go from 0 to the length of the box. So at the end of it, each of these particles from the position coordinates, what you will get is v to the power n, and this is exactly as you saw for the microcanonical ensemble as well. The indistinguishability factor is sitting intact, 1 by n factorial. And now the thing to note that is that since the Hamiltonian is e to the power I pi squared by 2m, what you have is basically this pi can be written as px squared plus py squared plus pz squared for each particle, d3p for each particle, and the coordinates are not coupled. The momenta coordinates are not coupled with other particles, right? So if you write, if you wish, you could write this as dp1x, dp1y, dp1z, and this Boltzmann factor can be written as e to the power minus beta p1x whole square by 2m, p1y whole square by 2m, p1z whole square by pm, sorry, 2m. So instead, what we write is like we have written this, and this goes on for each of the particles. And these are basically, if you think a bit about it, these are independent Gaussian integrals, because variables are not coupled with each other. Hence, this complicated looking integral, 3n dimensional integral in the momentum space with e to the minus beta h, where h is given like this, can be written as minus infinity to plus infinity if you're writing in px, py, and pz, which we have written as d3p. For each particle, this is the integral you have to evaluate to the power n, because the momenta of each of the particles are independent variables which are varying from minus infinity to plus infinity. Remember, when you were doing microcanonical, you had the condition that the total energy was fixed, but here the system can take any value of energy. You can have a microstate where p1, the x component of momenta, is nearly infinity, right? A very high tending to infinity, but that is possible. It's just that that microstate will have very low probability, or it will be weighted by a suitable e to the minus beta h, right? So thereby, the limits go from minus infinity to infinity, and the integral, this integral e to the minus beta h, can be broken over, or can be broken up into n independent integrals, and this makes it really easy for us. So here d3p, so this here we are writing as dpx, dpy, dpz, can be written as 4 pi p squared in the spherical coordinates. It's a spherical shell, into dp, where p is now is something like the dr. It's basically a scalar quantity, right? I mean, and so just look how we go from the Cartesian coordinates to the spherical polar coordinates, and that's exactly what has been done here. So this is 4 pi r square is the surface area of a thin shell into dp, and all that you're doing is integral, right? In spherical polar coordinates, these limits go from 0 to infinity. And that is exactly what has been done here. So this to the power n remains intact here, e to the minus beta p squared, where p is a scalar quantity which runs from 0 to infinity. Here pi was running from minus infinity to plus infinity, but here, since we are working in this spherical polar coordinates, d3p has been replaced by 4 pi p squared dp. The value of p can be only be positive and can go from 0 to infinity. Right? So that's what we have written this. Now, this quantity without the power n, let's call it at zp, and this is integral. It's a gamma integral which can easily be evaluated. And how does one evaluate it? So let's give the variable, so whatever is sitting there in the exponent, my beta p squared by 2m, let's call that x, and we are going to change the variables. So x equal to beta p squared by 2m, and we can write p to be, we can take 2m in this side of the equation, so 2mx, and this goes here, beta to the power half, and we can calculate dp suitably. So basically what you do is here, this entire quantity has been differentiated, hence this half minus 1 becomes minus half, and you have differentiated this as well. So that's why you get 2m beta here, right? And you get this half factor when you differentiate that entire part into dx, right? So finally, doing a bit of algebra, what you get is p square equal to 2mx by beta, and dp equal to m by 2 beta x to the power half, just by simplifying here into dx. So what you replace, so this p square you replace by 2mx. So note that we are calculating zp. Zp is just this variable, and later we'll put to the power n. That is just one of these integrals that we are calculating. And so it already had this 4 pi p squared. Now we are doing a variable transform. So beta p squared by 2m, we write it as minus x equal to beta p squared by 2m, right? Minus is intact, minus x. This p square we replace by 2mx by beta. This dp we replace in terms of the new variables, 1 by square root 2, 1 by square root 2, m by beta x, m by beta x to the power half into dx, right? This 4 pi is intact as it was there even here, right? So now if you simplify this, if you just carefully just work and simplify this root 2, this 2 will cancel. You had m by beta here and m by beta here, right? So this becomes m by beta to the power 3 by 2. On the other hand, here you had x, and here you had root x, x to the power half. This 2 and this root 2, you get root 2. So what you get is, after simplifying 4 pi m by beta cube, of where do you get cube? I'm sure you must have 3 by 2 here. So this is wrong. You should be having 3 by 2 here into e to the power minus x, e to the power minus x, x to the power half dx. And this, if you know, done your mathematical physics courses before, you might be knowing that this is called the gamma integral. And if you have x to the power half, so the gamma integral is e to the power minus x to the power n minus 1 dx 0 to infinity. So this is gamma 3 by 2. If you haven't looked up, if you don't know what I'm look of the expression for the gamma integer, and this is gamma 3 by 2, which gives half into gamma half, and this value is half pi. So you can easily integrate it, and thereby this integral zp is this zp, right? Mm, yeah. So what all that I've done is write 2 pi. So this 4 pi is written as 2 pi, and the 2, I think I've taken it inside from somewhere. Yeah, there was a root 2 here. This root 2 and 2 has been taken inside to write 2m by beta to the power 3 by 2, right? So this 4 and root 2 was there. That can be written as 2 into 2 into root 2. So that is come here. It's gamma 3 by 2. And finally, what you get after doing all this algebra is Zp equal to 2m pi kbt to the power 3 by 2. Note, the integral was over dp, the momenta, right? So here the integral was over dp, and thereby the z, the expression for z, what you get is 1 by n factorial v volume by h cubed to the power n. And since there were n particles and you had to do n such integrals, see here there is 3 by 2, what you get is 2 pi m kbt to the power 3 by 2 into n. Why? Because here there were supposed to be n, there was n such integrals which were multiplied and with each other because they're independent of each other. Thereby, when you do ln of z, what we have done is written ln of v by h cubed to the power n 2 pi m kbt to the power 3 by 2 n, and this n factorial by Stirling's approximation becomes n log n minus n. But since this was already coming as a minus log n factorial, what you have is minus n log n plus n, right? And the free energy can be written as minus kbt ln z. We had already associated the free energy with f and associated it with minus kbt ln z. And what we will see in 2 seconds or whatever 2 minutes is that if we associate f with minus kbt ln z for the Hamiltonian of a ideal gas, we can get back PV equal to nRT. So if we keep associating f with minus kbt ln z, where z was calculated here, ln z was calculated here, then what we get is n kbt, this n comes down, right? So what you have, because of this minus sign, now v is in the denominator, right? And this n is in the numerator. This n is in the numerator, and all these this h cube has been written as h square by 2 pi m kbt. You had this 2 pi m kbt, but now it is in the denominator. The h square has gone up and is sitting as h to the power 3 by 2. The consequence is this can be written as n kbt ln n by v, and this term h square plus 2 pi kbt, or if you like, you can write beta on the numerator, minus 1 can be written. So this is the expression for the free energy of an ideal gas, which has an Hamiltonian. This you can explicitly calculate the partition function. You can calculate explicitly the partition function, which is a function note of n, v, and t, whereas in the microcanonical system calculation, the number of microstates was a function of n, v, and e, But here you have a system which can exchange energy with the reservoir, and the system is defined by N, V, and T. So the free energy that you are getting is again a function of N, V, and T, right? And so this is the expression for the free energy for an ideal gas which you can calculate exactly. And once you have the free energy, you take a derivative with respect to the volume at fixed T and N, and that quantity was associated with the pressure with a minus sign. So if you just do that, so del V partial derivative of the free energy with respect to volume at fixed T and N with a minus sign. So this minus sign is coming here. And if you take a derivative with respect to V, so this minus sign goes in again, and you have ln V minus ln N minus ln this terms, but this term, none of them depend upon V. So when you take a derivative with respect to V, only this ln V contributes and gives a 1 by V, and as a consequence, P equal to NKBT by V, which is the ideal gas equation. Now, this was known previously from experimental considerations. But if we consider the gas that we see around us, which obeys PV equal to nRT, the ideal gas equation, if we assume that it has particles and it occupies different microstates, and its Hamiltonian can be given only by P square by 2m, but the system collides and keeps exchanging momenta, thereby it occupies all different microstates, and thereby you can calculate a partition function. Then using principles of statistical physics, one can calculate its partition function, and once it can calculate its partition function, can associate minus kBT ln z with f. And if we believe that this minus kBT ln z is really the free energy, and take a derivative with respect to volume, which gives P with a negative sign here, then using this expression, we can derive the ideal gas equation. So that's the interesting surprise of it. Moreover, we will take this ahead and calculate the equipartition theorem. So what was the equipartition theorem? The equipartition theorem, which you might have seen from the kinetic theory of gases, was that that each degree of freedom, the kinetic energy of each degree of freedom was associated with minus half kBT. Okay, so to do this, all that we are going to do is to remind you that we have already calculated the partition function for an ideal gas with a particular Hamiltonian. The assumption is these particles are colliding and accessing different microstates. As they are accessing different microstates with different probability, higher energy microstates are lesser probability. So we are using all that formalism to calculate the normalization constant, which was called to be Z, and associated F with minus kBT ln Z. Furthermore, we had shown that the average energy of the system, note this angular brackets correspond to the ensemble average, and that average energy over all microstates, we associated it with the internal energy. That's what we use to actually connect F with minus kBT ln Z. If you remember, just go back and look at your previous classes if you don't. But we also showed that the average energy of a system can be calculated by taking a minus single derivative with respect to beta of ln of Z. Right? The ln of Z, or F by kBT minus ln Z, is F by kBT, has this expression N ln N by V, H by 2 pi m kBT. Now note this kBT is 1 by beta, or 1 by kBT can be written as beta. So that is exactly what we are doing. Since we are going to take a derivative with respect to beta, we are collecting all different variables here, n by v, right? Minus ln z was this. We have kept n by v, h square by 2 pi m. However, this kbt, 1 by kbt, we are writing as beta, and to the power 3 by 2 was here. So that's intact. Minus 1 is coming from the Stirling approximation. So finally, we break down this log to two terms. One of the term has no contribution from beta. It's not a function of beta, whereas the other term is a function of beta, and this is minus 1. When we calculate the average energy minus del del beta equal to minus ln z, all that we have to do is take a derivative with respect to here. So 3 by 2 beta to the power half. Yeah. Yeah, and when you take the derivative with respect to ln, you get 1 upon beta to the power 3 by 2. And all that you get that the average energy of the system is 3 by 2 n kBt. Now, n is the number of molecules. If we want to write it in terms of n, the small n, number of moles, into R, so n can be written also into n into Avogadro's number, and then you will get 3 by 2 RT if you like, right? And of course, here constant volume, if you have calculated the energy of an ideal gas, room temperature, if it's an ideal gas, is considered to be 3 by 2 RT per mole. And if you have n particles, then it's n kBt. So energy per degree of freedom is energy by 3n equal to half kBt. By the way, this does not really show that each degree of freedom has half kBt. So that we will show in the next slide. Here, all that we are saying that if you have n particles, the particles can take any values of momenta, they can collide with each other, they can absorb energy from the reservoir. Each particle can have low velocities or high velocities, but the energy, I mean, whether that microstate is accessible or not depends upon the energy of the microstate, which is the sum of the p square by 2m of all the particles. And that's how we calculated z, the consequence of which, I mean, as the particles explore different momenta values and different energy values, and as the different particles explore different energy values, the system as a whole explores different energy values. So over all of this, and the systems collide, they exchange momenta, they are constantly evolving from one microstate to the other, right, as a function of time. But here what we have done is done an ensemble average. We have assumed that the system will go from different microstate to the other, and this collection of all microstates, different microstates with different values of the energy, they correspond to a canonical ensemble. The set of all possible microstates correspond to a canonical ensemble, and this average is over all the microstates of a canonical ensemble, because we have used that Z calculation and so on and so forth. And we had shown in the past that average energy of the system can be written here. If you don't understand this expression, again, please go back in one of the previous lectures. You can see that. And there we see that average energy per degree of freedom is half kBt, or the total average is given by 3 by 2 and kBt. Of course, we have to show that each degree of freedom individually also has half kBt, and that's what we shall show in just a couple of slides. But before that, what I want to emphasize is the following, that we got half kBt because there were quadratic terms sitting in the Hamiltonian, and the Hamiltonian was sitting is here. It is here, and the reason we got this half kBt, it might seem like magic, is actually is a consequence that we were able to do this Gaussian integral. Now, suppose we take, so we are not writing it in spherical polar coordinates anymore, but we are writing as minus infinity to plus infinity dx e to the minus ax squared. We're just discussing a Gaussian integral, right? Dx. Now, the value of this you can check it out is root pi by a. Now, when we were doing this thing when we were doing this integral, though we calculated it in spherical polar coordinates, you can also calculate it in Cartesian coordinates. And if you calculate this quantity, it will have pi to the power a, where a for our case is basically, this will be, I mean, if x was something like px square, we were doing dpx, this will be 2m kbt. Just think, I mean, the denominator would be 2m kbt, and thereby a would be 1 by 2m kbt. And this comes as pi by a. So what you get is 1 pi by this quantity, because a is 1 by 2m kbt, right? So I've written there. As a consequence, integral of this quantity, which is the one which we calculate, though I calculated it in spherical polar coordinates, is 2m kbt pi to the power half. So we could have also calculated this individually in dpx, dpy, dpz, and again we would have got, because you have an half here, then you have to take 3n, right? Would have get 3n by 2, and this is exactly the same expression. And the reason we are able to do this is because each of these integrals are independent of each other. Particle number 1's momenta does not depend upon the particle number 2's momenta, because it can take independent amount of energy from the from the reservoir, whereas that was not true for the microcanonical ensemble. So you can do the entire calculation again, and the total partition function will be 1 upon n factorial. So this, if you like, you can just break it down. Yeah, so this you can just break it down for the partition function, if you like, for one particle, that is Z1, and that can take volume V, and so on and so forth. It can take volume V, it will contribute C by 2, and so on. So the total partition function is basically, I mean, so this was for 1 degree of freedom, right, of x only. And then you can write it as 3n. So just be careful about this. I mean, I think this expression might be slightly wrong. I mean, because here I'm writing 3n, but then inside this, if there is volume also, there can't be volume. So this has to be written as, yeah, so this expression I'm pretty sure is wrong. Just be careful. This is correct. This expression is correct, but just think about it. Okay. The other thing I want to say, that in general, though we could write this each degree of freedom, I mean, we could write this quantity. No, sorry. This, for the kinetic energy, in general, we cannot write down. So this energy, average energy of the system, was only possible. This is really a contribution from the kinetic energy of the expression. This had no potential energy. If this had potential energy also, we couldn't write down the average energy of the system equal to 3 by 2 kBT. But since the momenta degrees of freedom do not couple with the positional degrees of freedom, note that we could still write the average kinetic energy of the system to be 3 by 2 n kBT. However, we could not write in general the average potential energy of the system to be 3 by 2 n kBT. So the average kinetic energy here, though it is the total energy, but here there is only the kinetic energy. There is no contribution from potential, right? Hence, we are writing the average energy of the system. This is also the average kinetic energy of the system. Only in this case, only because it's the ideal gas, that it is equal to 3 by 2 nkBT. And this came out as a consequence of the Gaussian integral, because in the Hamiltonian, the kinetic energy is coming in as p square by 2m as a quadratic. Now, if the potential energy of the system also had a quadratic term, only then, only if the potential energy had a quadratic term and it was not coupled with other degrees of freedom. Well, if it was coupled, we will come to that later, but if it was not coupled, then each of these half kx square would also contribute half kBt, right? So then, so suppose they were not coupled, so there were, suppose, an oscillator sitting, and so there was oscillator, but oscillator was with half kx square along each direction. It was not exchanging energy with its neighbor. If it did, then there would be a coupling term, but it can exchange energy with the reservoir, say, right? In that case, you would have, in terms of the partition function, for one particular particle, e to the power, only considering the x direction, px square by 2 mkbt, and here you would have half kx square by kbt again, right? And in this case, a would have be the value kappa by 2 kbt. So when you calculate this integral, this contribution from 1 degree of freedom would give you 1 by h cube. Of course, you would need to have an h cube here, 2 mkbt pi to the power half. And if there are n particles, then there would be n. If there were 3n degrees of freedom correspond to x, y, and z, then there would be 3n. But suppose you just have just x dimension, hence n, right? No 3n unless you have y and z as well. And here again, so this was n by 2, this n and a, and here this integral would give you, considering a equal to this quantity pi by a, 2 pi kbt by kappa to the power n by 2. And in this case, only when you have this case, n harmonic 1D oscillator, right, fixed in space, they're not coupling with each other, space coordinates are not coupled, momentum degrees of freedom are not coupled. So N1D harmonic oscillator fixed in space but can fluctuate about mean position, taking energy from the reservoir. In such a case, the average energy of the system will be nkBT. But again, this is nkBT because the contributing term from the potential, for the potential, was quadratic. If it was not quadratic, you would not have done this Gaussian integral and you would not have got half kBT for each degree of freedom contributions from the potential energy. The kinetic energy would still be, it would be still half kBT into n, because anyway momentum doesn't couple, but the potential could, but here it doesn't, and hence you are getting nkBT. With that, I will end this class and it will continue from the next class, especially discussing about the average kinetic energy for one particle, and to show that that will also be equal to half kBT Up till now, what we have calculated is for n particles, and we have shown that to be 3/2 nkbt. So this is slightly different. So let's stop here.